tutor for digital circuits. Thanks for coming to the my first ever exam review. This will be as much an experience for you as is for me, hopefully. These slides are full of new examples that I came up with. They are handwritten because they're pretty last minute, but I hope that I can still present them in a way that helps you learn. And I also have one example from Dr. Basu's slides over the Quine-McCluskey method. But yeah, we can go and get started. Oops. Cool. I hope you guys know all of your logic gates. This is all from the original digital systems class. It makes sense. Here we have the min terms and max terms from truth table. This isn't animated, but basically the min terms of the function are going to be where the function has a 1, and the max terms. Wait, my bad, guys. The let me go ahead and pull up the definition. But min terms are what you're going to be using when the function has a 1, and the max terms are going to be when the function has a 0. Your min terms are used for the sum of products, and the max terms are used for the product of sums. Okay. Here we have all of the Boolean algebra formulas, and this is the tricky one where the inverse of the product is the same as the inverse of the sum is the same as the product of the inverses, and likewise the inverse of the product is the same as the sum of the inverses. I've got a little example going over Boolean algebra for a quick little review for this first test. So here we have a function with 6 variables, AB bar plus CD bar plus EF bar. And I want to put it into the canonical forms of POS and SOP. And then I want to simplify it down as far as it can go. So the first step to this is we're going to use our, I forgot the name of it, but the one where, which one? De Morgan's principle. Thanks. It's the one where you're going to invert the whole function. So here we invert the inversion, which gets rid of this top bar. And then each of our terms gets inverted and it becomes the product as our first step. And after we do that, we can further simplify it down. So we apply a De Morgan's once again to each term. So AB bar quantity barred will become A bar plus B, and these products still remain here. You once again apply the inversion down to CD bar, you get C bar plus D. And once again, if you apply it to the bar of E and F, you get E bar plus F bar, which is just a direct application of De Morgan's. And this is the POS form. It's as simplified as you can get because there's no duplicates of any of these variables. But if we want to turn it into the SOP form, we have to start distributing. So if we use FOIL on our A bar plus B over the C bar plus D, we can end up with, this term times the E bar plus F. And if we distribute once again, we can end up with these 8 terms, which make up the SOP form, or the sum of products. Normally, you'd look for any simplifications that can occur, but this one is as simplified as it can get. You see that each of these terms has no term with one difference. So for example, A bar B plus AB, there's only one difference between those two terms, in which case you'd be able to simplify it. All of these terms are unique, so they cannot be simplified. So that is SOP and POS. The next tool for logic simplification is the Karnaugh map. They can be presented in a few different ways. This is the one from Dr. Basu's lecture. The most significant bit is here, followed by the second most significant, third most, and least significant. You can also see it presented this way, where it's kind of rotated 90 degrees, where your most significant bit's the top, and then onwards down. And you can see each value corresponds to a number, and each number corresponds to a specific combination of logical variables. As you know, Karnaugh maps are really, really useful, and it allows us not to have to muddle down into the Boolean algebra. So we got a quick example of our Karnaugh map. We want to simplify the Boolean expression with the K-map method. And you can see here that this is a product of sums notation, not a sum of product, which means that each of these numbers tells us where we have a 0 in our expression. And I also have noticed that using product of sums is typically harder for most students than sum of products, just on the way how the variables distribute. It's very intuitive when you're working with a sum of products, but it's often unintuitive with a product of sums. So the first step is to fill in all of the zeros when you're working with a product of sums. You have a 3, 5, 7. This is the same for any table. If you're using Dr. Basu's table, it's just going to be rotated 90 degrees. This is the table that I always do. But after you fill in the zeros, the next step is to start circling. So you'll want to circle all combinations. You want to make the biggest circles that you can. So right now, the biggest circle that I see is this A and C naught circle, as well as this A and B naught circle. They have to be either 1 by 1, 1 by 2, 2 by 2, 2 by 4, or 4 by 4. Moving forwards, my animations are gone. That's hard. Okay. Well, here we have the A and C naught. So it's the same as if you go back to this one. These little lines tell us where the variable is 1, and where the line isn't there, the variable is 0. On this chart, when it's on the same side as the letter, it's considered a 1. When it's on the opposite side of the letter, it's considered a 0. So here we have this is A and not C. Likewise, animations are being really weird. Okay, here we go. So this one is A and C naught, because this one is A and this is not C. This other next biggest one is A and B. So A is 1 here. Sorry, and this is B naught. There's no B here. This one, it's not A, it's also B, and it's also D. And finally, this last one is a wraparound, which students often miss because all the sides of the K-map are connected. So this one is not B, this one is C, and it is also D. Cool. So from that, we can write our product of sums. And to do that, we invert each variable. We write them as a sum. So the A naught C is going to be A naught plus C. And we're going to do the same for each term. The A B naught becomes A naught B. The A naught BD becomes BD naught plus A. And the BCD, the naught on the B, puts the naught on the C and the D. And this gives us the most simplified version of our sum of products. Sorry, product of sums. But here, if we want to do the sum of products, instead of writing the zeros, like here, we write all the ones, and we start circling. So the biggest on this one is going to be right here, which is the A naught and the D naught. It's a 2 by 2 square because it wraps around the bottoms and the sides. Then we also are going to have a naught, B naught, and C naught right here, and an ABC right here. And to write this as our sum of products, it's really easy. We don't have to do any inversion. We just write them as a product and make them a sum. And for the last step, get out of the way, I ended up writing it as a logical diagram. Here, the little circles that you haven't seen before are inversion. So this right here represents the A, B, and C term where they're not inverted whatsoever. And this represents the A naught, B naught, C naught term, which all get multiplied or added together. Sorry, added, ANDed together. And this AD inversion as well. And then they get summed together. Sorry, not summed. They get ORed together with the OR gate at the end to give us our logical function. So
I have a question about the compacted form that you wrote it in.
Yeah.
Would that not be called the canonical sum of products or products of sum?
So I believe it's the most simplified verb. Sorry, this is the most simplified product of sum. Sorry, sum of product. I think the canonical form is its full expansion. So if I take this A naught D naught, I would have to write it as A naught D naught AB, A naught D naught AB naught. I would have to write every possible combination of A naught and D naught.
And how would you convert that to the compacted
form? Honestly, I would probably use a K-map. So right here, this is an expression of the canonical form. So it's for each of these numbers, it's representing that individual combination of logical variables.
So as in, if you were to take that answer, look only those variables and then convert it back into a compacted form.
Wait, say again?
So if you were to take
let's go to the end. Okay.
The answer
Yep.
and then use the summation, how would you put that in the summation compacted form?
Yeah. Honestly, probably using a K-map would be another good idea. So you go back to the version that came out with the numbers. First one. Okay. So basically what I would do is I'd mark a 1 for every possible combination where a 1 exists. So for example, if we have AB, right? So A is a 1 in this bottom half and a B is a 1 on this middle section. So all these would be marked with a 1. And I can repeat it for every single sum of product. And at the end, we'd have a K-map full of 1s, just like here. And then after that, all you have to do is find the number corresponding to each square. And you can end up in a form just like this. So, but yeah, that's how you do it. K-maps are really useful. You'll be using them all throughout this entire course, multiple times. They're just a very, very important skill. So, cool. Moving on, I know Dr. Bossi really likes word problems. So I came up with a new word problem that can hopefully prepare you for the exam tomorrow. Here I wanted to design a light bulb logic circuit where the state of the light bulb is controlled by 2 switches. So one example, this might be a household stairwell. We have 1 switch at the bottom of the stairwell, 1 at the top. We only have 1 light on the stairwell. And it's a requirement here that the state of the light bulb be changed by either switch, regardless of the other state of the switch. So to do this, well, that basically allows the person at the top of the stairwell to turn the light on if it's off, and at the bottom they can turn it on if it's off, or off if it's on. And the other thing that I wanted is if the switch A is on and B is off, the light bulb's on. If we only had the first constraint, there'd actually be 2 possible solutions to this problem, but adding the second constraint means we only have 1 logical function. So to start, this is our truth table. We're going to start filling it out. Here, if light switch A is on and if B is off, we want the light switch to be on. This was a constraint given by the problem. Likewise, if we turn the switch A off and B is still off, the light switch would turn off, which makes sense. So the next question is, if the light switch is already on and B was off, and we flip B on, what should happen to the light switch? So if you imagine if B is the top of the stairwell and the light switch is in this position right now, it's already on. We flip the switch in B, we want to be able to control the light. So if this is a 1, we won't be able to control the light because switching the switch does nothing to the light bulb. So this actually has to be a 0, which means now if we're at the top of the stairs, the light bulb is on, we can switch the light bulb off and we can turn the light off. Likewise, for this final case, if A is basically if we are in this case where the light bulb is off and we want to turn it on, right? So we're switching from this state to this state, the light bulb has to turn on. So we end up with this truth table for how the light bulb works. And we can rewrite it in our standard form, counting from 0, 1, 2, 3. Hopefully you guys can recognize this truth table. It's a very common one. It's the XOR truth table. But if you didn't know it, you could write it as AB naught plus A naught B. And then this is the Boolean logic form for XOR. And then here we have the gate, where it's A being XOR with B to get the light switch. So that's how those little light switch circuits work. They're pretty simple, they're pretty fun. You'll probably have problems like this on your exam. The last thing I want to get over is the Quine-McCluskey method. It is an annoying method to use. It takes a lot longer than the K-map, but it's really good for computers because the process is so standardized. There's no guess and check. It's very algorithmic. So if you guys are working your homework and you're checking your answers with an online program, it's using the Quine-McCluskey formula to simplify your logic. So here we have, sorry, I wanted to use this one. Here we have a function written in the sum of products form. We also have 3 don't cares. So the steps of the method, the first thing we're going to do is we're going to write all of these things out and group them by the number of 1s. So here you can see this one requires 4 groups of 1s. We have 0 1s, 1 1, 2 1s, 3 1s, and 4 1s. The ordering within the groups doesn't matter, but it makes sense to do them from least to most, so you can better keep track of things. But moving forward, the next step is to find combinations of logic where there's only one difference between the 2 states. So if we're comparing the row with 0 1s to the row with 1 1, right? The 0 0 0 versus the 0 1 0 0, there's 1 bit of difference between the 2, which is happening in the second place. So then what we're supposed to do is we take it, we realize the difference is there, and we write it in a new column with a dash representing where the difference was. And this is basically equivalent to when you're working in just with straight Boolean algebra, when you're finding combinations of variables with only one difference, where you factor out the difference and you rewrite it with one less term. So we finish comparing the 0 zeros to the 1 zeros. We notice that this one also has 1 bit of difference. So we also write it with a dash in the right column. So after you compare 0 with 1, you compare 1 with 2. Here we see that 0 1 0 0 has 1 bit of difference with 0 1 0 1. It's in this 4th place. So we write a dash in this 4th place. Then we finish comparing the 2nd column to the 3rd column. So it's good to compare 4 to 5, 6, 7, to 5, 6, 9, 10 all at once, and then compare 8 to 5, 6, 9, 10 all at once. And you end up with dashes in each place. And then you compare the 3rd to the 4th, and then the 4th to the 5th. And after that, you end up with a 2nd column, which is full of things with little dashes. We also want to group this column again by the number of 1s. It's an iterative process. Computers love iterative processes. Humans less so level iterative processes, so it takes a lot of paper space to make it work. But the final thing to do is to once again look for entries with 0 bits of difference. So what's up?
It's the importance of the checks and the stuff.
Yeah. So previously we're checking off to make sure that every single logical combination makes it into the second column. But here, the stars represent logic combinations which can't be further simplified. So if we look at 0 dash 0 0, there is nothing in the 1 1 section that has 1 bit of difference between the 0 1 section. Because we can't find any matches, they have to show up in our final decision making.
The prime implicants, right?
What?
Those are the
yes.
prime implicants, right?
Yeah. Thanks for the term. Similarly, you can see the 4 5 and the 4 6 term. They vary by 1 bit. Sorry. The position of the don't care. So because they are all the same except for the don't cares, they get smushed together, and we can add the don't cares together, which gives this term. Likewise, when we come down here, we see that the 5 7 and the 13 15, the 0 and the 1 are the only bit of difference, which is why they appear up in here. But you can see that the 5 13, 6 7, and the 7 15 all have check marks. That's because these are all covered by the 5 7 13 15 prime that we found in column 3. So there's no reason to write the 5 13 and the 6 7 over in column 3. Sorry, because they already appear over here. So after you do all of this, you end up with a list of prime implicants. And using the prime implicant chart, we can turn this into a complete logical function. So what we're going to do is for each prime implicant, we're going to check off which min terms they cover. So for example, the 0 4 case has a don't care on the second one, which corresponds to 4. Likewise, the 4 5 6 7, they cover the 4 5 6. But you notice that there's no 7 here. That's because the 7 was a don't care. So the don't cares help us with the logic simplification, which all happened in the previous step, but they don't help us when we actually figure out what min terms we have to cover with our prime implicants. So they never get included on this last table. If you accidentally include them on your table, you've messed up. You're going to get the wrong final logical solution. So it's important to note that when you get to this stage. So the goal of the Quine-McCluskey method and all logic simplification is to cover as many min terms with the fewest number of prime implicants, which means we're going to want to use this 4 5 6 7 term, and we're definitely going to want to use that one because it covers 3, right? And we're going to use whatever else we need to cover the remainder of the min terms. So after we have this one, we end up covering the 4 5 and 6. And this one can cover the 8 and 10. And then it's also selecting, it's telling us the ones that we've covered after we select these 2 rows. These are represented by the blue lines. So it's telling us we only need the 9 and the 13 left. There's only one function which covers both the 9 and 13, which is the 1-01, which can be covered by that line. So we can see we can cover all of the min terms required for the logic with these 3 prime implicants. So the final step is to turn the logical combinations with the dashes into their actual representation as Boolean functions. So the way to do that is if there's a 1, it's not inverted. If there's 0, it's inverted. The opposite is true when you're working with product sums. So you can see here, the A bar B corresponds to the 0 and the 1. This corresponds to this one, sorry, this corresponds to this one, and this one corresponds to this one. But yeah, that's the last slide I have of the actual review. So I was hoping to have the last 30 minutes be questions, and hopefully I can answer them. I have all the slides from Dr. Basu. So if you have a question, I can pull up the slide and explain that part a little bit more. So you guys have any questions? I apologize if it was not very great of an explanation. But.
I have a question.
Okay.
So like, if you are given the McCluskey, right, and want to solve through it, but they give you the POS, so like the pi instead of the sum,
Yep.
would you just convert it back to the SOP and then do everything?
No, so the best way to do it, let me go back. It's basically going to be just like a, give me a second. I have to go back to the very start. It would probably be best to convert it to SOP. So while the K-map method would be really native to the K-map method would work really well with POS, but this method doesn't really care about this initial interpretation. It only cares which values are 1. So yeah, you'd have to convert it, which would just be pretty easy. Yeah.
So just to be clear,
Yeah.
That's a sum of midterms, so it wants a sum of midterms home. And then if we get some of max terms, and in order to change it, you have to do the De Morgan's. So if the don't cares with just 0 or 715, and you knotted the sum of max terms, what would happen to the don't cares? Would they not be affected? Or anything like that?
So you're asking if you're converting between SOP and POS?
Yeah, and then if there's
What would happen to the don't cares?
Yeah, what happens?
They would just stay as don't cares. So if you're starting, sorry?
It could be either 0 or 1.
Yeah, so they stay the same. So if you're starting with like, 0 to 15, if there's a 0 here, okay, I can just convert this one actually, use a pen. So 0 would stay. This one doesn't have a 1. There's no 2 in this list. There's no 3 in this list. There's a 4, 5, and 6 in this list. I would write 7, but the 7s don't care. So the 8, 9, 10 are in the list. The 11 isn't. The 12 isn't. 13's on this list. The 14 isn't. And the 15s don't care. So if this were to be converted from the sum of products to the product of sums, you would do that, and then you include the original don't cares. So if you had it in a pi instead of a sigma, that's how you convert between the two. This is a good question. And yeah, good.
I have one more question about the McCluskey process when you get to the table.
Yeah.
Every time they've gone over it in the notes, they kind of just skip through it with the covering. If you could we go over that again, and maybe like
The third column one?
no, the cover.
Oh, yeah.
I found that to be a little.
Okay, the way the lines are drawn is a little weird. It is confusing the way the lines are drawn. I'll draw new lines. So first off, this one covers the most prime implicants, so we want it. Right.
So we don't do it by singular. I thought
What do you mean?
the singular prime implicants. Isn't that how we're supposed to do it?
So what do you mean the singular prime implicants?
Maybe I like the vertical single ones. Am I correct?
That might be a better method. So you mean this one only gets? Oh, I see what you mean. Yeah,
Probably, yeah.
that's a good method. Let me erase. I erase. Okay, it's whatever. Yeah, so M6 only is covered by one possible prime implicant, so it has to be included, which means this comes in here. So these are all included. Next up, M10 is only covered by one prime implicant, which means that these two get covered, and this comes here. So these are the vertical lines. All of these minterms are covered, which means that there's only two minterms left that need to be covered. You could do it with 8, 9, and you could do it with this last one, but that wouldn't be as efficient as using the 9, 13. So that's how you end up with.
So just to reiterate, we go over the vertical lines which cover the horizontal, and then whichever ones they cover, vertical lines go out of those, and then we pick out whichever ones are left. That happens to be the ones that go
Yeah.
horizontal.
That makes sense. I figure how to
Kinda,
erase.
like, minimize it, I think.
Yeah, because on the homework problem, every single one just happened to be the correct one,
Yeah.
I think.
Yeah, it was all of them.
Um,
Yeah, I remember that actually when I took this.
Sometimes it happens, it's all of it.
But he told us on the exam, it will not be that easy.
I can go over this process again, but with his notes, which might be useful actually. So I can stop sharing. Start a new share.
Right?
Yeah, it could be a bonus problem, I'm sure. You would,
There you go, 4 questions and 1 bonus. I don't know, maybe.
Quine-McCluskey algebra on the exam.
Verilog.
that'd be hard.
Yeah.
Let's see. Yeah, that's great. Okay. Okay. We can go over Petrick's method if you guys want. That one seems pretty useful. Okay. So here's another prime implicant chart. I'll go ahead and go over this one again. So you want to start out with the ones that only have a single associated prime implicant. So this minterm is associated with this function. And likewise, the minterm 24 is associated with this prime implicant, which means this column's covered, this column's covered, and this column's covered. Okay. This one is kind of like the homework problems, but likewise, you can go down and this only has one possible function, which is this one, which means all of the columns which have an x get covered. And then once again, there's only one on here. This one's kind of like the homework one, right, where it all gets covered.
So we pick every single one?
What?
Pick the second one.
Or only the horizontal ones?
Only pick first row, third row, fourth row, fifth row.
Because the second row is redundant by the first and third.
Or we pick the horizontal ones?
Yeah, just.
Yeah.
The 0, 1, what dashes, those are the ones we use
Yeah.
to write the equation.
Which means if you wanted to turn this into the actual Boolean expression, this first one would be A. We don't write the B because it's a dash. C. D. Oh my goodness, my handwriting. Ald. Yeah, we do that for each one. We don't have to see. That's kind of the conversion that takes place.
A not, C not, D not.
Oh, here it's an E naught actually. Yeah, another line.
Do a 13
What a
variable
amazing
K-map.
In my brain, it's like playing 4-dimensional chess with those high-dimensional K
Dude,
maps.
it's 3D.
I like it.
Even the professor told us he has never done that. Seriously.
And it's just
Yeah, once you go to like 5 variable, it just like expands into another word.
It's like
Yeah.
solving those 3D circuits, like the non-planar circuits.
Mhm.
We should have a either the one.
He said it was gonna be 4 variables.
I really don't think he's going to give you a lot.
He was making it easy for us. I love that.
Easy.
this is a 5 variable, but it's a not a came out. But yeah, that's it. Patrick Smith is kind of cool. I don't know if it's gonna be on your exam or not. It's not. Okay. And there's no need to talk about it. It's not on the exam. It doesn't matter. That's one thing I learned being an engineer. Yeah. Any more questions from online? No. Oh, I don't hear anything. They're all muted. Well, thanks for coming, I guess. I hope you do well tomorrow. I was saying earlier, the people that showed up here today are probably in a much better position. Not because of my great presentation skills, but because of the fact you guys showed up. But yeah, that's it. Thank you guys for coming. My tutoring hours are on Monday. There are plenty of other digital circuits tutors as well. Those are posted on the Discord. So definitely come to tutoring. Good luck with your exam on Thursday, guys. Take care.